Hey everyone, here we are for notebook page 11, which is going to hit the rest of the senses: touch, taste, smell, and position. So if you need to take down the title card, please do so now. Let's get rolling. So let's start with touch. Touch is a sensation that detects pressure, temperature, pain, etc. So when things are touched, your sensory neurons are activated, sending neurochemical signals through the peripheral nervous system to the central nervous system, through the brainstem to the parietal lobes for interpretation. So it goes through all those different systems when you touch something. Regarding pain, however, the prevailing theory is that of gate control, that small fibers and nociceptors, which are sensory receptors for painful stimuli, constantly send pain signals to the central nervous system. So essentially, your body is always in pain, and these nociceptors are always sending that signal. But the gate part comes in because the large fibers that constantly block that signal. They're blocking that signal from getting to your brain. When stimulated by actual pain, it's believed the large fibers open the gate, swing it open, and allow small fiber pain signals to be passed on. This is then interpreted by the brain as pain. This means that pain itself doesn't actually exist. It's an interpretation of neurochemicals by the brain, meaning our brain can create its own pain in dreams by misinterpreting other sensory information, and the lining of the nociceptor can also deteriorate, which results in the constant sending of small fiber pain signals. So that's what happens when you have multiple sclerosis. The linings of those receptors deteriorate, and those pain signals keep going and go through that gate. You know, an example of misinterpreting other sensory information to cause pain is phantom limbs, phantom pain, something we'll get into. That, in war situations, often if someone loses a limb, a leg, an arm, they will still feel pain. They'll still feel pain between their toes of a leg they don't have. That shows that pain isn't quote unquote real, that it is interpretation of neurochemical signals. So we'll get more into that here in a second. Let me put up the slide now. And take us down. Let's move on to slide 2, pain management. So based on factors such as genetics, psychological distractions, chemical influences, and something like endorphins, can actually cause some to experience pain more or less intensely, meaning that pain is not felt equally. I won't feel the same pain that you feel in the same situation. Pain can be managed in multiple ways, including medically by mimicking endorphins with substances like opiates and ibuprofen, hypnotism, massage, exercise, acupuncture, even placebos can be used to treat pain. Touch, like the other senses, can be impacted by one's own thoughts and psyche. So, and your touch can shift your intuition and impact your cognition and judgment through a process known as embodied cognition. This is the confirmed notion that if you're holding or touching warm surfaces, you are literally more likely to act friendly and warm, whereas the same is true of holding or touching cold surfaces, kind of the opposite. If you're holding something cold, it'll make you likely to act more reserved or cold. So that is embodied cognition, something that touch can actually influence how we act. And, back to kind of how pain is treated, there's so many different ways because it's just that interpretation of neurochemical signals. There isn't one specific way to treat pain. And so, often, and because it's different for each person, that level of pain is very different. So there's still a lot of exploring needs to be done scientifically about pain. It's something that is being done now, but it's a little bit more difficult. But take us down now. Let's move on to slide 3, taste. The taste occurs mostly on the tongue, but it also is an interaction between one's smell, olfactory recognition of chemicals, so your nose recognizing chemicals, as well as texture, bump lines on the tongue. They line the entire top of your tongue and descending to the back of the tongue. On each bump are over 200 taste buds, each with a pore that contains 50 to 100 chemical taste receptors, with each taste bud's receptor being more or less sensitive to one of the 5 tastes: sweet, sour, bitter, salty, and umami. So you may have heard the first 4: sweet, sour, bitter, and salty. But umami has recently been found to be there. Umami is a seldom known flavor. It's described as kind of brothy, savory, tomatoes, bell peppers, seaweed, things like that. Taste can be impacted psychologically, as one's perception of food they're eating, appearance, smell, information about the food can impact the flavor, or at least the enjoyment of the flavor. So, for example, there was a study done where they had same meal, some type of chicken meal for people, and had them rate how good it was. One, the control group, they just ate it, rated it, right? Pretty simple. The experimental group smelled a artificial scent of rotten chicken, rotten meat, before they ate it, and rated it much, 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 much lower. So that smell can impact how you look at things. They've done this with even appearance and plating and things like that too. Let me put up the slide. All right. Slide 4, olfaction. No. First, before we get to that, here's what the taste buds look like. If you want to take a look at these and see you can see that the taste pores here, and how taste kind of goes through the basal cells down through the connective tissue, so that you get these taste receptor cells take in the taste, they send that back to the brain. That's how you know how things taste. So now olfaction. Smell occurs through the detection of chemicals by odorant receptors in the olfactory membrane located in the upper regions of the nasal cavity. So much like neurotransmissions are only activated by certain chemicals that don't fit any receptors can't actually be smelled. So we have about 10,000 smells that we can roughly smell. If the smell is not within those 10,000 or a combination of them, then it cannot be smelled. It won't have a smell. That's why things don't have smells. They might give off a scent that our brain can't interpret. The neural signals are sent by the odorant receptors to the olfactory bulb, then to the brain for interpretation. Depending on the sequence and combination of activated odorant receptors, the olfactory cortex determines the smell, much like scrambling letters to form words. The human olfactory system is able to experience about 10,000 smells, like I said before. And psychological factors can impact olfaction, as one's less likely to enjoy smells which are associated with unpleasant experiences. For example, in the United Kingdom, people tend to dislike the smell of wintergreen more than in the United States, because in the UK, it is used in medicine to hide the taste of medicine. Whereas in the US, we have gum that's wintergreen, we have candy that's wintergreen. It's a little more higher on the pleasantness scale. So that can have an impact psychologically as well. And it can even be personal, in terms of a bad experience you have associated with a certain smell. If you had someone had a hard night drinking a lot of alcohol, they drank screwdrivers, they drank orange juice and vodka, and they had so much they got incredibly sick, throwing up. The next day they wake up, they smell orange juice, they're going to be sick again. Smell brings that back. We've talked about that before. So that they might not like the smell of orange juice for the next 5 years. It could be. So it can have personal experiences as well. Slide here. Write this one down there. And here's how smell works. right? Here's the take in the scent in that nasal cavity. The olfactory neurons will take in the scent, push it through the olfactory bulb, up into the limbic system, and that's how we get our sense. Let's do kinesthesia, slide 5. Kinesthesia is knowing where the parts of your body are, even when not moving them. So it's connected to the vestibular sense for motion and balance, which monitors head position. So it's kind of an odd sense, not one that we talk about often, but a very important one, because if you don't know where your limbs are when you can't see them, you're going to fall over. You're not going to be able to walk. You're going to have problems. So you have to have the sense of where those are. We'll take a look later at someone who does not have, who has learned to adapt but didn't have that sense and what that looked like. So to manage our balance, semicircular canals and vestibular sacs residing next to the cochlea contain fluid that moves when your head rotates or tilts, so you can keep your balance even when you're rotating your head. This movement stimulates hair-like receptors, which send messages to the cerebellum to determine your balance and stability. So that happens. Why sometimes you can lose balance if you have ear issues, since it is that kind of cochlea that is helping with balance, and all these combined can have issues. Let me put up a slide here. You can go and write this down now. And that's it for this notebook page 11. You got it down. All is good. Thanks so much.